As you can see, the title of tonight's talk is The History of Hydraulic Fluid Power, but since we've got 226 years of history to get through, it'll only be a fairly brief history, I'm afraid, but we'll get through as much as we can. Hydraulics is a term that means different things to different people, so just to clarify things, what I'm not going to talk about tonight is anything to do with dams or hydroelectric power, rivers or river estuaries, or even water wheels. What I am going to talk about is basically the transmission of power through machinery in industrial applications such as presses and injection molding machines and machine tools, things like that in industrial applications. Also, of course, in mobile applications, we've got things like JCBs and other diggers, we've got combine harvesters, we've got forklift trucks and so on. So it's the transmission of power, basically, which is why I tend to call it hydraulic fluid power rather than just hydraulics, to avoid any possible confusion. So where did it all start? Well, I guess we can go back really to the ancient Greeks, the guy called Ctesibius, who was working in Alexandria in Egypt a couple of centuries BC. And he was the guy who really invented what we call the positive displacement pump, or piston pump, as it's known today. Basically, he had two wooden pistons reciprocated by a hand lever inside two bronze cylinders. And by means of some leather flap valves on the inlet and the outlet of the device, he got a more or less constant flow of fluid out of the nozzle. And then if we move on a couple of millennia, or a millennia and a half, Leonardo da Vinci got pretty close to describing hydraulic systems, but he had so many ideas and so many inventions up his sleeve that he didn't really have time to pursue it. And then in Holland, Simon Stevin, around about 1586, really defined what we mean by hydrostatic pressure in a fluid and explained how it varied with the depth of the fluid. But it was really down to the French philosopher Blaise Pascal in the middle of the 17th century, who stated that pressure is transmitted undiminished throughout a fluid and acts with equal force on equal areas at right angles to the areas. So basically what he was saying is that pressure can go around corners, if you like. But he also proposed a machine for using pressure to multiply force. And he said that if we had a small weight acting on a small diameter piston, that could easily balance a much larger weight balanced on a much larger piston. So what he'd done basically was to explain the hydraulic equivalent of a mechanical lever. We can do exactly the same thing if we have a small weight acting on a long lever arm that can balance a much larger weight acting on a small lever arm. So that became known as Pascal's law, say in the middle of the 17th century. But it took almost, or slightly over 140 years before anybody made use of that principle. It just sort of sat there and nobody did anything with it until a Yorkshireman called Joseph Bramah came along and patented the first hydraulic press. You can see on the right-hand side there in 1795. Why it took quite that long is a bit of a mystery. Obviously, there were practical problems to overcome, such as the sealing of the pistons and this sort of thing. But they weren't enormous problems because, as we said, pumps had been made before with sealing leathers and so forth. But as we said, it was really Joseph Bramah who kicked off the whole hydraulic industry when he patented the first press in 1795. And to illustrate his press illustration, he used a pump piston diameter of 1/4 of an inch, which is the piston diameter here, acting on a larger piston in the center of the press, which is a 12-inch diameter piston, plus a bit of mechanical advantage from the lever on the press pump. And he reckoned he could get an output from this press of just over 2,300 tons, which was pretty impressive from a wooden press. And if you work out the sums, that works out to a pressure of 46,000 pounds per square inch. Well, just to put that into perspective, the first aeroplane to use a hydraulic system at 5,000 psi, which was the Airbus 380, which first flew in 2005. Up to then, all aircraft had been using 3,000 psi systems. So for the very first hydraulic machine to use a pressure of 46,000 psi was perhaps a tad ambitious. But nevertheless, it was just an illustration in his patent application. But probably more importantly, in the same patent application, Bramah illustrated another use of hydraulic fluid power, which was to actually, not just for force multiplication, but to actually transmit the power over a distance. And he just illustrated a simple arrangement here with a hand pump and a cylinder ringing a bell. And that really is the main use of hydraulic fluid power today, is to act as a power transmission medium rather than just a force multiplier. So in the early days of hydraulic fluid power, that's what it was used for in presses, for squeezing things together, such as baling cotton and baling wool and hay and so forth, and later on for forging metals and so forth, as we'll see. A couple of years after his patent, 1797, we know that this is one of the first presses that Bramah actually made. His patent illustration was probably no more than that, just an illustration. But this one is documented in a book by William Nicholson. It's a much more modest affair than his 2,300 ton press. It was a 1.5 ton press used in the book manufacturing industry for pressing books together and so forth in the manufacture. Made out of cast iron, no doubt, rather than wood, but a much more modest machine to start off the whole industry, really. These days, of course, you can dip down to Halfords and for 16 quid, you can buy yourself something very similar to that, which works on exactly the same principle. Just a simple little bottle jack with a hand pump, using exactly the same principle that Bramah used in his early presses. 10 years on, things had got a bit bigger, and this is a press that was installed initially in the Tower of London for use in the manufacture of maps. It saw a varied life, ending up at the Ordnance Survey Works in Chessington, but it was in continuous use for over 160 years. It was only in 1966 that it was eventually pensioned off. So he did a pretty good job with it, considering it was only 10 years after the initial patent. The hand wheels on either side of the press are just basically for closing the daylight area, so that you didn't have to pump the whole thing up right from the bottom of its stroke. You could do a rapid advance on the hand wheels and then just use the hydraulic pump for doing the final squeeze on the material. We know quite a lot about this press because it still exists. It's been preserved, and it's now exhibited in the Kelham Island Museum in the middle of Sheffield. So it's not actually functioning, but it's still in full working, well, not working order, but still in good condition on display in that museum, which is well worth a visit if you're ever up that way, because they've got some impressive other things to look at as well. When Bramah's patent ran out, everybody else seemed to jump on the bandwagon. Matthew Murray, for example, up in Leeds, came up with this double acting press that you can see on the left-hand side there, using basically rack and pinion arrangement to get movement on both the top and the bottom platens to save a little bit of time in the pressing process. Also, downstroking presses came along as well. The advantage here is that you didn't have to lift up your bales of hay or wool or cotton, whatever it is you were compressing, up onto the top platen. You could do it more or less at floor level. But because cylinders were only single acting at that stage, you then had to find some way of retracting the cylinder, retracting the piston at the end of the working stroke of the press. And in this particular case, it was done by counterweights on either side of the press platen. The other main use for presses at this time was in the extraction of oil from seeds. Before the oil fields opened up in Philadelphia in the middle of the 19th century, if you ever wanted any oil, then it was derived from either animals or from plants. And it was quite expensive. If you need it for lubrication or for making paint, for example, it was quite an expensive commodity. So pressing seeds, typically linseeds or flax for linseed oil, for example, was a big industry, especially around East Yorkshire, around Hull area and so forth. So this was the other main use for hydraulic presses at that time. So as I said, yes, the other main use, apart from baling up cotton and hay and so forth, was for extracting oil from seeds. And this is where it was a more or less continuous process. So rather than having a poor chap pumping away on a hand pump all day long, they tended to connect the pump to an overhead line shaft so that they could mechanize the whole process, if you like. So this just illustrates it a little bit further, where they've taken standard hand pumps, connected via a connecting link to an eccentric on the overhead line shaft, and got the whole process mechanized to be more efficient. Quite an interesting application, though, came up in America with a guy called Joseph Francis. Tended to dry out in the sun over a period of time, so the wooden planking tended to shrink, and the first time you put the boat into the water, it tended to leak like a sieve. So not one of the attributes that you're looking for really on a lifeboat. So he came up with the idea of using a metal one, corrugated iron lifeboat, which he made in a hydraulic press using a male and female mold, if you like, two halves of the mold, again just operated by hand pump. The boat was made in two halves, and then he just riveted the two halves of the boat together. So he ended up with not only a lighter lifeboat, but one that didn't tend to dry out and leak. Later on, things got a bit heavier, and in the forging of crankshafts for large steam engines and so forth, the Scotsman James Naismith came out with the steam hammer, which was basically a bigger version of the blacksmith's hammer. He used a steam cylinder at the top here just to lift up a heavy load, heavy weight, and then by dropping it with a bit of assistance from steam pressure on the top as well, it came thumping down onto the component at the bottom, which whatever it was you were forging. But you can imagine that these things did make their presence known in the neighborhood when you've got a 3 or 5 ton weight bashing down on a heavy forging several times a minute. Then you knew that the machine was operating. Especially when they got to that sort of size, which was the largest steam hammer, I think, that was produced, 125 ton version over in the States. So a guy called James John Haswell came up with the idea of using hydraulics again for the forging process. And in conjunction with the Kirkstall Forge Company up in Leeds, he designed the first hydraulic open forging press in 1862, which then, instead of just hitting the workpiece with repeated hammer blows, it gave a nice steady squeeze to the component, which not only gave you a better quality forging, but was also less intrusive on the neighborhood. In fact, it was stated that a lady in a muslin dress could stand close to it and incur no risk. These days, of course, the lady would also need a hard hat and high-vis jacket and some safety boots as well. But there you are. Again, we know quite a bit about Haswell's press because it still exists. He moved on to become the superintendent of works for the Austrian railways. So he obviously took his press with him, and it ended up in the Technische Museum in Vienna, where it still resides. The biggest press in the world today is one in China. It's an 80,000 ton die forging press, so not something you want to get your finger caught in, really. It's a pretty huge animal, weighs 25,000 tons and absorbs something like 42,000 horsepower, operating over a pressure of just over 9,000 psi. It's got 5 main cylinders and 25 auxiliary cylinders for doing different things on the press. And the compressed volume is something like 500 gallons. That's not the volume of fluid in the press itself. It's the extra volume you have to squeeze in to build it up to 9,300 psi due to the compressibility of the fluid. People tend to think of fluids as being incompressible, but they're far from it. In this case, you can squeeze an extra 500 gallons in. And in the process, the massive columns of the press stretch by over an inch. So it's a pretty hefty affair. In fact, if you turned the whole thing upside down, you could quite easily lift the weight of the new Queen Elizabeth aircraft carrier together with a Type 45 destroyer placed on its deck. So, as we said, it's a pretty hefty piece of equipment. Okay, so as well as using hydraulics for presses, it was also employed for other uses as well, in particular for cranes and so forth. Bramah himself had designed and developed a workshop crane not long after his initial patent, just basically using a rack and pinion arrangement again with a hydraulic cylinder turning a winch drum for lifting components in his own workshop. He stated that it could raise and lower its load 15 or 20 times a minute to a height of 18 to 20 feet. Well, again, if you do the sums, that works out to an operational speed of something like 13 feet per second, and probably sounds as feasible as his 2,300 ton wooden press. So he was obviously a bit of an advertising man, was Joseph Bramah as well. The man who really developed the hydraulic crane was William Armstrong up in Newcastle. And this is really what set him off and is what became a huge business in the end of the century. He developed what's called the hydraulic jigger, which is basically a series of pulleys attached to a hydraulic cylinder and really operates in the opposite way to a block and pulley, if you can imagine it. He's using the high force output of a hydraulic cylinder and then multiplying the movement using the pulley wheels and so forth to get a larger movement out of the end of the crane. There are still a few of these jiggers around if you look carefully in St Catherine's Dock in London, I think, and this particular one here is in Albert Dock in Liverpool. Some of them have been preserved and still in situ. Jiggers were also used on what's generally considered to be the first hydraulic excavator, which was developed by a guy called John Aird in 1882. And it was used during the hydraulification of Hull's docks. I'm not quite sure if hydraulification is a word, but if electrification is, then I don't see why hydraulification shouldn't be. You probably recognize that ship. If you don't, the title of the slide gives you a bit of a clue. But to build a big battleship like HMS Victory, it took something of the order of 6,000 trees, of which 90% were English oak trees. So it was a big requirement for wood in the end of the 18th century for shipbuilding. And Bramah had the idea of, rather than chopping down the oak trees, which left a big stump in the ground and hindered the replanting process, why not just pull them up by their roots? He wasn't just talking about pushing them over, as we've illustrated here, but actually just manually, bodily lifting the tree out of the ground by its roots. And if you do the sums again, you'll find that he could well have done that. He had enough hydraulic force to actually bodily lift a tree out of the ground, and therefore not only provide more wood in the process, but say clear the ground ready for replanting. The only problem is we don't know how he did it. There was a fire in Bramah's factory in 1843, and a lot of his early records were lost in that fire. So there is no record remaining that I've been able to find, at least, of exactly what this machine looked like for pulling trees out of the ground by their roots. We know that he'd developed a device for removing piles from the ground, from riverbeds and so forth, which looks something like this illustration here. So whether it was adapted for pulling trees up, we just don't know. If you do an internet search for removing piles, it takes you down another avenue altogether, unfortunately. As well as lifting, we also have a machine here for lowering. This one is situated in Kensal Green Cemetery on the west side of London. And it's possibly, as far as I can make out, possibly the world's oldest working hydraulic machine, because it has been restored to working order now. And it was basically a lift or a lowering device now, taking the coffin of a deceased person from the chapel in Kensal Green Cemetery. By opening up a simple valve, the coffin could then be lowered slowly and gracefully and silently into the catacombs below. So, say this has now been fully restored. You can find a video of it on YouTube if you're really interested. And it's, say, possibly the oldest working hydraulic machine in the world now. They wouldn't let me take any pictures of it when I was down there, but these pictures are of a very similar installation in West Norwood Cemetery, which, as you can see, is still in situ and still pretty well complete, I think, but it hasn't been restored. So that's something like what the Kensal Green Cemetery system would have looked like. Okay, so moving on to bridges. What's hydraulics got to do with bridges? Well, before we had air travel, of course, if you wanted to travel from the mainland of Britain over to Dublin, then the way you went was via sea from the port of Holyhead. And as you probably know, Holyhead is on an island. And to get to the island, you have to cross a very narrow stretch of water called the Menai Strait. Well, Thomas Telford had built a bridge across the Menai Strait, a road bridge across the Menai Strait in 1826. But when they wanted a rail bridge, they thought that a suspension bridge probably wouldn't be stiff enough to carry rail traffic. So Robert Stephenson of railroad fame was engaged to design a rail bridge. And after much deliberation and trial and errors and so forth, he came up with basically what was the first box girder bridge, using a rectangular section tube strengthened by compartments top and bottom, and supported along the way by stone piers. Each of the four central tubes was 460 feet long and weighed something like 1,500 tons by the time it was fully assembled. So you've got an up line and a down line, as you can imagine here. They're fabricated on the shore because the Admiralty wouldn't let them put up scaffolding to impede the process of ships through the strait for any length of time. So they were constructed on the shore in wrought iron sections being riveted together. They were then floated out on a couple of pontoons and then dropped onto specially built ledges built into the towers. When they dropped them onto the ledges, just as an indication of the sort of clearances that the Victorian engineers worked to, they found that over the 460-foot length of the tube, they had just 3/4 of an inch clearance at each end. So they were used to working to pretty close tolerances. All they had to do then was to lift the tubes up into the position 100 feet above the high water mark. So again, they did that using hydraulic power. Each 1,500-ton tube was lifted 6 feet at a time by a big hydraulic cylinder, where each lift took about 45 minutes, pumps being operated by 2 steam engines. The cylinders were pretty massive components. The ram diameter, the piston diameter in the cylinder was something like 20 inches and had a wall thickness of something like 11 inches, weighing a total of 16 tons. In fact, when they took them out of the mold, it took 3 days for the cylinder casting to cool down before they could machine it. But they weren't quite massive enough, because on the first lift of the first tube, they blew the bottom out of one of the cylinders with a hydraulic pressure and dropped the tube something like 9 inches back onto the supporting beam. Again, we know that because the bit that blew out of the bottom of the cylinder is still there on the side of the Menai Strait. The bridge took something like 4 years to build, employed an army of workmen, and cost almost £250,000 in 1850, which is something like £33 million today's money. Oops. But it was destroyed by 2 teenage boys one evening in 1970. They'd gone inside the bridge tubes to search for bats or something like that. I think they lit some paper to see where they were, and the tower inside the bridge caught light. It had a wooden ceiling to it, wooden roof on the bridge, and that eventually caught light as well. So the whole lot went up in flames. The bridge strength was then really compromised by the heat of the fire, so they decided that they could no longer use it for rail traffic. So between 72 and 1980, it was rebuilt using steel arches, since it no longer was a requirement to have high-masted ships sailing underneath it as it was initially. But it lost a lot of its elegance in the process, I think. They also added a roadway to the top of it as well. Okay, so hydraulics had been used extensively in the construction of bridges, but there are many bridges that actually move as part of their working life as well. In particular, the swing bridge across the River Tyne in Newcastle. This was built to enable Armstrong ships. His factory was upstream of the bridge here. So it had to open to allow Armstrong ships to get access to the sea. Again, it was all hydraulically powered, and again, the equipment is still there, still in everyday use. Apart from the fact that the pumps are now driven by electric motors rather than steam engines, everything else is the original Armstrong equipment and still in full working order. Perhaps the most famous moving bridge, though, is Tower Bridge across the River Thames in London. This consists of 2 bascules either side on either tower, which open and close whenever a ship taller than the bridge itself needs to go through. They again are operated hydraulically. Armstrong again supplied most of the equipment originally for the operation of the bridge, and each bascule is counterbalanced by a heavy load on the rear of the bascule here. And then it's opened and closed by means of a hydraulic motor acting on this curved rack arrangement. So it's a rack and pinion arrangement again, but using a curved rack rather than a straight one. Tower Bridge opened, literally in this case, on the 3rd of June, 1894. It had its first failure on the 1st of July, but it was the 1st of July, 1968. Over 74 years after it first opened. In that 74-year period, it had opened and closed successfully over 350,000 times, which is not a bad record really for a Victorian bridge designed for pedestrians and horse-drawn traffic and so forth, and which is now ton lorries going across it, of course. These days, we talk in terms of Six Sigma reliability, which allows for one failure every 300,000 opportunities. And if you can get something that reliable, then you're doing pretty well. You're pretty well world class, 99.9997% reliability. Well, as we can see, the Victorians achieved that and more well over 100 years ago. Okay, moving on to look at ships. When Brunel turned his hand to shipbuilding, the first one he came up with was the Great Western, 2,300 tons. As it turned out, it was meant to be the first steamship to cross the Atlantic, but as it turned out, it was the second steamship to cross the Atlantic, beaten by a day by one of his rivals. Around about 7 years later, he came up with the Great Britain, which was larger still. This is the one that was scuttled in the Falkland Islands for many years, and then towed back to the UK in 1970, and subsequently restored, and now resides in the dry dock where it was built in Bristol. But both of those were really mere tiddlers compared to what was going to be his crowning glory, the Great Eastern, 1859, which was 19,000 tons. That was built on the side of the River Thames in Millwall. It suffered from no end of problems, economic problems with companies going bankrupt and so forth. But eventually he got it finished, and one of the cutbacks that had been made was in the launching equipment. So when they took the chocks away, they weren't quite sure whether it was going to slide down the slideway all on its own, or whether it would need coaxing and shoving and pushing down there. Well, when they took the chocks away, it slipped a few feet, but then stopped. So they got their answer then, it was going to need pushing. So they scoured the country for every hydraulic cylinder that they could find and every hydraulic pump, and Robert Stephenson even loaned Brunel the cylinders he'd used for lifting the tubes of the Britannia Bridge. So inch by inch, they hydraulically pushed the big ship into the water, but it took them about 3 months to do so. And finally, in the January of the following year, they finally got it into the water and floated away. Henry Bessemer also came up with a rather interesting design for a ship. He'd had the idea of creating a mortar shell that would spin and therefore improve its accuracy, but without using a rifle barrel in the gun barrel. He used basically some drillings in the mortar shell and came out at a tangent basically, so that the explosive gases would actually act to spin the shell as it left the barrel. He tried it out in his back garden, and it was stated that the gun was fired at an angle of 45 degrees. The projectile reached an estimated height of 200 feet and revolved like a Catherine wheel before hitting the ground, still within the boundary of the garden. So obviously Bessemer had a decent size back garden. He took the idea to the War Office, but they weren't really interested in it. So he took the idea then across the channel to the French, who were fighting on the same side as us at the time. They were interested, but they reckoned that their guns weren't strong enough, their cast iron guns weren't strong enough to make full use of the idea. So with no doubt a sigh, he came back and basically invented the mass production of steel to get around that little problem that the French had with their guns, where he basically designed a big converter vessel, and no doubt inevitably known as the Bessemer converter, which was filled up with molten iron initially, and then air was blown through it for about 20 minutes or so. And then the whole vessel was then tilted up on its end to release the molten steel into a ladle. So again, pretty hefty piece of equipment that had to be moved or spun round in this case. So again, he employed the use of hydraulics to do so. Hopefully that animation will come out on your screens. And these converters were mounted 2, 3, or even 4 up on cattle sometimes to get a more or less continuous supply of steel. And again, as he wrote in his autobiography, the mode of transmitting semi-rotating motion to the converter was another important problem which I had to solve. 5 or 10 tons of fluid metal had to be lifted in one direction, this load diminishing until the fluid running to the opposite end of the converter tended to reverse the driving gear. If anything went wrong or slipped, the converter might swing itself round and discharge the incandescent metal onto the floor or among the work people. So basically what he did was to use, again, a rack and pinion arrangement with a hydraulic cylinder, this time with the rod of the cylinder stationary and the outer casing, the cylinder of the cylinder barrel was the moving component. And again, as he stated, these considerations led me to adopt the hydraulic apparatus now universally employed for governing the motions of the converter. With a simple and reliable means, a lad at a safe distance can start and stop it instantly. You can alter its speed and motion and control the pouring of a 10-ton charge with ease and certainty. So this is obviously the beginning of the health and safety regime, because the lad who was operating this was located at a safe distance. Anyway, what's this got to do with ships? Well, in the process of selling this idea to the French, he was traveling backwards and forwards across the channel quite regularly, and he wasn't a very good sailor. He suffered from seasickness quite a lot. So he designed and built a steamship which would counteract the effect of seasickness by having a cabin in the center here, which was hydraulically operated either side, and therefore could counteract the effect of the ship rolling. He tried to do it on the pitching motion of the ship as well, but that proved a bit too complicated. So he resigned himself to just compensating for the roll of the ship by 2 hydraulic cylinders operated by a sailor using an equilibrium valve, as he called it, which was so easy of motion that a child could work it, especially if they'd had experience of controlling 10-ton converter vessels, no doubt. To counteract the effect of the pitching of the vessel, he made it as long as he possibly could, 350 feet, which was then too long to turn round in Calais Harbour. So he built it double-ended with a bow on either end so it could sail backwards and forwards across the channel without having to turn round. But it wasn't a huge success. The two did actually cross the channel. It wasn't really rough enough to try out his cabin, so he scrapped it off at the end of the day. You may remember a few years back, a ship called the Costa Concordia capsized and sank off the coast of Tuscany. Well, again, it was hydraulics that was used to bring that back to an upright position, mounted to mount onto a cradle, which was built underneath here to stop the whole thing slipping down further into the sea. They welded canisters on the side here, were filled with seawater to try and bring the thing back to an upright position. But in addition to that, they used something like 60 strand jacks, creating 336,000 tons of force to also pull the thing back to an upright position. Strand jack is quite a simple device. It's hydraulic cylinder in the middle here with some hydraulic clamps top and bottom. And it uses exactly the same principle that Stephenson had used for lifting the tubes of the Britannia Bridge. You clamp at the top, pull up the wire ropes through the device. The cylinder then retracts. You undo the clamp at the bottom, clamp at the top, and pull the rope up a bit further. So bit by bit, you can lift whatever it is you're wanting to raise. So exactly the same principle that Stephenson had used to lift the tubes of the Britannia Bridge. You've no doubt come across these devices, simulator rides that you can go on to pretend you're flying with the red arrows or driving a rally car or whatever. Again, we tend to think of these as modern devices, but again, the Victorians had something even grander. At the Paris Exposition of 1900, a guy called Hugo de Lacy didn't bother with just a simple little caravan on hydraulic cylinders. He used a complete ship, using hydraulic cylinders fore and aft for the pitching movement and either side for the rolling movement. And the ship could carry something like 700 people at a time. They didn't have video projection in those days, so to create the illusion of movement, he had two very large rolls of canvas either side of the ship, which were rolled up on these rolls at fore and aft, painted with scenery, appropriate scenery, and these were gradually rolled across to create the illusion of movement. And there was a bit of smoke and steam blown across it as well, some thunder and lightning created, and faint smell of seaweed and tar, all to create the illusion of sea travel. So that was known as the Mariorama, say in 1900. Boat lifts for lifting boats between waterways. One that's recently been returned to operating condition is the Anderton boat lift up in Cheshire, not far from Northwich. Links the River Weaver to the Trent and Mersey Canal. And it basically used two pontoons which were interlinked. So the weight of one pontoon lowering would more or less balance the weight to be lifted in the other one. It was hydraulically operated initially with two large cylinders underneath, but they gradually got corroded and it was replaced. They were replaced by electric drive, but it's now been fairly recently restored to hydraulic operation again. And the other famous boat lift, I guess, is the Falkirk wheel, coming a bit more up to date. This one links the Forth and Clyde and Union canals up in Falkirk. And unique design, really. It's a rotary boat lift, but again, hydraulic power just to turn the thing around, just to overcome wind forces and a bit of friction and so forth. One of Bramah's ideas was to have complete hydraulic ring mains. Initially, he envisaged them running around dockyards and so forth, but eventually these got big enough to run around complete cities. Notably London and Birmingham, Liverpool, Manchester, and so forth. This shows you the map of the largest one, which was known initially as the Wharves and Warehouses Steam Power and Hydraulic Pressure Company. But fortunately, they changed their name shortly afterwards to the London Hydraulic Power Company. And this was a map of what they eventually looked like in terms of their network of hydraulic pipework operating at something like 700 PSI through 6 or 7 pumping stations. So it was quite an extensive network, really. That was the sort of typical pump that was used, initially steam driven, but most of them were converted to electric drives later on. Typical 3-throw ram pump was used to basically charge up large accumulators in there so that they could even out the pumping requirement as the demand for hydraulic flow varied these large accumulators, which was basically just a hydraulic cylinder turned up on end with a weight put on the top of it to store fluid under pressure, could be used to provide an instant supply of power when needed. Vehicles. The first vehicle that was really converted to hydraulic drive used a brand new technology, which is known as an axial pump, shown here, which was developed around about the turn of the century by two guys called Harvey Williams and Reynolds Janney. Basically, it was a completely new concept using what we call a swash plate type pump, where you had an angled plate in the pump here, which was driven around by an electric motor or a diesel engine, whatever it happens to be that's driving the unit. And that created a reciprocating movement of the pistons in the pump here as they went round and round. That was connected to a hydraulic motor, which was basically the same thing on the other end, but operating in reverse now. In case of a motor, you're supplying fluid to it under pressure in order to turn the shaft round. So by varying the angle of the shaft, they could vary the amount of fluid that was pumped and therefore vary the speed of the motor on the other end. And if they go over center on the swash plate, they can actually reverse the direction of the motor. So what they ended up with was a variable speed drive, which was not only variable speed, but also reversible as well. The motor was a fixed angle plate here on the left-hand side, but the pump swash plate was variable, could be tilted backwards and forwards. So if you reduce the angle of the pump plate, you reduce the speed of the motor. If you got the plate into a vertical position, then the motor stops. And if you start tilting it the opposite way, then you reverse the direction. So to say, a complete variable speed, reversible drive. And similar units are built today, of course. It was tried initially on a truck drive, mounted down underneath the chassis of the truck here, so driven by a prop shaft from the truck's engine. The drive to the wheels then came out at right angles rather than in line. And it proved successful from a technical point of view, but it just wasn't successful commercially. It was just too expensive for use on trucks. But it did find a use on ships for roading the gunboats on battleships and so forth. And that's really when this technology took off. It was also tried out on some of the heavy tanks at the end of World War I, right at the very end of the war. These tanks were driven by a huge petrol engine, something like a 19-litre petrol engine. In the mechanical drive arrangements to turn the tank, to steer the tank, you had to declutch one of the tracks of the tank and probably stop it in the process as well. Turn the tank round and then set off again. So it was a bit hit and miss, a bit jerky. But the variable speed drive meant that you could just slow one track relative to the other. So it became much easier to steer the tank. It could be steered on the move as well, and was therefore a great improvement over just a straightforward mechanical drive. So you had two pumps operating from a power takeoff from the petrol engine, each one driving a motor on the tracks of the tank. So as I said, it was a technical success again, but it came right at the very end of the war, so it wasn't developed in any sense. So moving up to the modern day then, if you mention hydraulics to the average man in the street, I guess the thing that they associate with hydraulic power is probably the JCB digger. It's the one that everybody sees out on the roads, digging up holes in the road and so forth. Joe Bamford designed the first, what we call backhoe loader, to give it its true name, back in the early 50s. And that's what the first one looked like. If you compare to what they look like today, it doesn't look that much different. A bit more comfortable, I guess, and they've got DVD players and CD players inside the cab and air conditioning now, but the basic function of the machine is still much the same as it was 70 years ago. So it was a pretty good design to start with, and just about every function on the machine, apart from the transmission, is hydraulically powered. Man lifts, or scissor lifts, or cherry pickers, whatever you like to call them. These again are a typical application for hydraulics, where the drive, the wheels, and also the lifting cylinder itself is hydraulically powered. These days, they're full of health and safety equipment to stop people falling off and stop them getting their arm trapped in the scissor arms and stop them crashing down to the ground and so forth. But it wasn't always that way. Going back to the early 60s, the first man lift, as illustrated here, was just basically that big telescopic cylinder and a hand pump. So health and safety in those days wasn't quite such the consideration that it is today. Those sort of machines required valves to be operated remotely. So this saw the advent of what we call solenoid operated valves, where instead of a guy grabbing hold of a lever and pushing a spool across in a valve manually, they mounted electrical solenoids to the end of the valve so that it could be operated just by flicking a switch. If I can get the thing going backwards and forwards, yeah, just by opening and closing switches to the electrical switches to the solenoids, you can now control the valve and therefore your direction of flow remotely. So these were the early solenoid valves appearing in the 1950s and thereabouts. They're a bit more sophisticated today, but basically it's still a spool moving within a body to control the direction of flow. But now they have a lot of built-in electronics to provide much more accurate and sophisticated control over the flow, and they've got built-in sensors to sense the temperature and the pressure of the fluid and so forth. And they may have complete axis controllers built in as well these days. So again, you can do all of your controlling built into the valve. You don't need separate electronics to do your closed loop control. It's all built into the valve itself. You just need a PLC or something like that to sequence it, tell it when to stop and start, and the valve thinks out all the movements for itself. So that's the sort of thing that you find in wind turbines these days. Hydraulics is used not only for the braking of the rotor when the wind speed gets too high and you have to shut the wind turbine down. You have a disc brake that clamps it solid, but you also have to vary the pitch of the blades to keep the rotational speed of the turbine more or less constant, irrespective of the wind speed. So that's done by varying the blade pitch here. And again, that's done by means of hydraulic cylinders up in the nacelle here, controlled by these sort of valves. And then the final illustration is just something that you tend to find on shipborne systems these days. It's what we call a heave compensation system, where you've constructing pipelines or something like that, and you want to compensate for the weight on the ship itself, which could be moving up and down several meters. You want to keep the end of your cable more or less constant within a centimeter or two, or even if it's just a gangway connecting a ship to a platform or something like that, then you can use what we call an active heave compensation system, where you have a motion reference unit controlling the electronic valves, which in turn are controlling the winch, the hydraulic motor on the winch. So all sorts of sophisticated applications today. So we've come a long way in the last 226 years, from Bramah's 1.5 ton hand-operated book press to the 80,000 ton die forging press of today. Just wonders where we will go in the next 200 years. So there we are, 200 years of history in an hour and 3 minutes. Hopefully it's, apart from a few snags on the technical side, hopefully it's been of interest.
Yes, indeed. Well, thank you very much indeed for an amazing trot through 200 years. Has anybody got any questions? Perhaps if we go back to if you stop your screen share, and we'll go to a gallery view, people could ask questions. If anybody got a question, you have to unmute yourself. I'm afraid the unmute facility was taken away some time ago by Zoom. But if anybody wants to ask a question, perhaps wave an arm about. Yes, John Cartledge has a question.
Can you tell us a bit more about the London Hydraulic Power Company? How long did it operate? Sort of how many customers did it have? When did it pack up, if it packed up? And how competitive was it with alternative source of power like electricity?
Okay, well, it set up towards the end of the 19th century. It was the first power company started up in Hull, which was a sort of a prototype system, if you like.
We're losing you. Perhaps you turn your camera on.
Somebody said if it had been installed 10 years earlier, it would have got a lot bigger. If it had been installed 10 years later, it probably wouldn't have been installed at all, because electric drives would have taken over. But it lasted until 1976. Tower Bridge was, although it had its own hydraulic power supply, it was also connected to the London Hydraulic Power Company supply as well as a backup. So it lasted from the end of around about 1894, I think, up until 1976. A lot of its downfall was caused by the Luftwaffe during the Second World War, which destroyed not only some of the pipe work, but also a lot of the customers. And of course, a lot of the customers tended to move away from city centre location. So eventually it came to an end, I say, in 1976, and the tunnels and the pipe work was sold off to one of the telecommunication companies for use of laying cables underneath the City of London. So it was pretty successful. Not quite 100 years, but getting on that way.
Wouldn't it be very vulnerable to leakage from the pipes?
It was, yes, especially in wintertime when the water in there was freezing, of course. It was usually the job of the apprentices employed by the company to go around and collect all the horse droppings from the streets and use that to lag the pipes, the water pipes, because it was water that was used in these systems, of course. Sometimes they added a little bit of alcohol in there as well as an antifreeze, but most of the time it was pure river water. So they did tend to suffer a little bit from frozen pipes in the wintertime. But yes, there was a certain amount of leakage from the pipe work, and that's why the system used the large accumulators to compensate for that to a certain degree.
How
many customers they had? Sorry, go on.
I say, if you walk around Docklands, you can see there are some builders and accumulator towers still remaining.
That's right.
Through Docklands, you can see some still.
You'll also find some equipment there marked up with London Hydraulic Power Company.
An interesting final use for them was that in the early days of fibre optics, they used the pipe work for transmitting or taking the fibre optic cables through London.
That's right. That's right. When London Hydraulic Power Company finally gave up business, they sold all the pipe network to I forget the name of the company now, but yes, they used the pipe work for. Sorry.
I think it was Cable and Wireless who bought it.
It could well have been, yes, yeah. So they used the pipe work that was already there for running their cables to avoid digging new holes in the ground, I guess.
We had at the Rickmansworth U3A meeting, engineering meeting last week, we had a very interesting talk, a tour around the Underfalls Yard in Bristol, which has got a hydraulic network, and they are quite enterprising. Their trust run, the man, one of their employees, went round with his mobile phone giving a talk of the whole yard, including a Victorian workshop, and he got that going and various things, overhead shafting on that. But he then went into the hydraulic yard, and they've got an accumulator tower there with a large weight, or a large cylinder full of lumps of metal, which are steel to make the weight, and he got the pump going and showed the thing lifting up and down. It was quite an impressive working, and it worked all. And what he was looking for was some hydraulic device, such as a crane or something, that he could use to demonstrate how the hydraulic power worked, because the hydraulic things that like the lock gates and everything else have been taken away. But that was what he was looking for. So
yeah. It's not all that long ago, I think, that the lock gates were removed. It's quite recently, I think. But yeah, there is still a lot of equipment around, especially around Liverpool docks. Say that the picture of the jigger that we saw earlier on was from Albert Dock in Liverpool. The Grimsby Tower, of course, is one that Armstrong built for powering the hydraulic equipment at Grimsby docks. Or most of the equipment for the Tower Bridge operation is still in situ. It's no longer working. It's an oil hydraulic system now that works the bascules of Tower Bridge. But most of the original water hydraulic equipment and steam engines and so forth are still in situ. And you can actually go around and see them and photograph them if you want. So there is still a lot of equipment still around.
Colin, you have a...
When I've unmuted, I used to work for a company that made these sort of hydraulic jacks, etc., for a company called Redifon. And they used to do the aircraft flight simulators. So, of course, you had about 5 or 6 jacks operating these platforms, when mixed with solenoids, with computers, with everything. And of course, practically every aircraft operating company in the world uses these simulators, because it's obviously a lot cheaper to crash your simulator than it is your aircraft. So, but these were made to an incredibly fine tolerances. They were very expensive, but a piece of sophisticated hydraulic work, I don't think I could think of anything greater.
That's right. Yeah, they use something called servo valves on the actuators there, which were very high performance solenoid type valves, if you like.
Yeah.
Very, very rapid operation and so forth. But you're absolutely right. And the simulators are still used today, of course. And the sort of the Fairground Red Arrows ride is a derivative from those simulators. In fact, the Fairground ones are somewhat tend to be more demanding than the aircraft simulators, in that, you know, people, when they fly with the Red Arrows, they expect to be jolted around all over the place, whereas the pilots being trained are looking for a nice smooth landing and takeoff of course. So the Fairground simulators are in some ways more demanding than the real thing. But you're absolutely right. Yeah, it's a classic application for servo valves in hydraulic systems.
Anyone else got any more questions?
Yeah, Steve.
Yep.
Do we know what that monstrous Chinese 80,000 ton press is used for?
It's used, as far as I'm aware, for producing aircraft forging. From titanium and aluminium alloys and this sort of thing. I haven't seen a great deal about its use. I think they're a little bit secretive about what they do use it for, but it's mainly for the aerospace industry.
Okay.
Creating, say, forging. Certainly the big presses that were produced in the States, and they got sort of 50, 60,000 ton presses in the States now. They are used for fighter aircraft forgings and so forth.
Right. Do you think
it's not
that's
something
a
you want to
likely
catch your finger in?
Oh, we didn't hear that. Sorry, say again.
Do you think that is a likely explanation? Was aircraft are mainly made from aluminium? Wouldn't have thought they need 80,000 tons.
It's possible, yes, because they do produce quite large forgings. The other possibility, of course, is for the nuclear industry as well. But I haven't seen anything definite on there. But it was rumoured that they were producing forgings for nuclear reactors.
Okay. Thank you.
Okay. Anyone else? No? Well, thank you very much indeed, Steve, for a very interesting evening. And,
okay, Chris.
Thank you very much. And
sorry about a few hiccups along the way.
Not at all, as these things happen. It's still fairly new technology. Will we in 200 years' time be talking about how we're holding our meetings via the newest version of Zoom, Directly, whatever.
Right, yes.
Okay, well, thank you
very
much.
Holograms then.
Yes. And I'll say that completes the
thank you.
of our